So welcome everyone again for the second session of the day 2, and we have another eminent speaker with us, Professor C.C. Reddy from IIT Ropar. So I'll just give and it's an honor for me to introduce Dr. C.C. Reddy, Associate Professor, Department of Electrical Engineering and Associate Dean, Student Affairs at IIT Ropar. We are very privileged to have you here, sir. And just to give a brief intro about Professor Reddy. So Professor C.C. Reddy is one among the few researchers working in the extremely interdisciplinary field of high voltage engineering and its applications. And he possesses immense experience, practical as well as theoretical, in the field of electrical power cable technology, nanodielectrics, and space charge in dielectrics. To brief his professional background and accomplishment, I'm glad to share that before joining IIT Ropar in 2011, he was a senior R&D engineer in Ultra High Voltage Research Lab of J Power Systems Corporation, Hitachi, Japan. Dr. Reddy has published more than 100 papers in peer-reviewed international journals and the conferences such as IEEE, IET, and IEEJ. In the field of nanodielectrics, power cables, power transformers, bushings, mechanism of breakdown, space charges, and conduction in dielectric materials. Until now, he has guided 4 PhD students to their defense, and currently he is guiding 10 PhD students apart from several master's and bachelor's students. He has also authored a book on reliability and life estimation of power equipment with New Age international publishers. Moreover, he is working as well as he has worked on several projects with private industries like Reliance, Adani, etc. And apart from that, he has also been working with some several public industries such as CPWD and CPRI. I'm very happy to share that he has been the organizing chair of IEEE CATCON 2017, General Chair of IEEE ICIS 2018 and 2020, General Co-Chair of IEEE ICIS 2017-2019, and TBC Chair of CATCON 2020. And most importantly, he has been an international advisory member of prestigious symposium on electrical insulating materials ISEIM since 2011 that is being held in Japan. He has been a prominent member of Bureau of Indian Standards Subcommittee on Electrics, member of Board of Studies of several universities in India. Dr. Reddy has also participated in academic industries, collaborative research in Japan with several universities of Japan such as Toyohashi University, Waseda University, Tokyo City University, Osamu University of Technology, and he has participated in deliberations of Technical Committee, Standard Committee on Space Charge Measurements in Dielectric Materials. Lastly, it is with immense pride I wish to inform that he is an associate editor of IEEE Transactions on Dielectrics and Electrical Insulation. Again, sir, we all heartily welcome you. And Dr. Reddy will be sharing his experience, expertise, and knowledge in the field of electrical power cable technology. Over to you, Reddy, sir.
Thank you. Thank you, Palash, for the introduction. Thank you.
Thank you very much, sir.
All faculty members at NIT Warangal for inviting me here. So it's a great privilege for me to give my presentation on electric power cables. So without much delay, I would like to start my presentation. I will share my presentation.
Yeah, sure, sir.
I think you can see, right?
Yes, sir. Yes, sir. It's visible, sir. Perfect, sir. Perfect.
Yeah, so this is a presentation on power cable technology. So I will be introducing the power cable technology basics in this lecture. It's not a core research presentation, but it helps a lot for faculty working in engineering colleges, and you may consider in future to add some portions of it in your high voltage course or any power system course also. So certain important aspects which are not normally taught at engineering level are given here. So these of course are gaining importance due to smart power systems. So the power cable technology, power cables are essential part of any smart power systems. So this I start my presentation. These are the references you may go through from which we have taken the materials, including our own research also. So smart power systems cannot be achieved without power cables. So we shall just see the reasons for that. So you can see the transmission and the distribution. The middle portion is a distribution system in old Delhi, reported in Daily Mail, UK. So you can see how clumsy the distribution network is, and in open space on an overhead distribution system. And at the right and left also you can see how many wires are hanging in open space. So a modern smart city cannot afford to have such awkward distribution network, and a smart distribution system must use underground power cables. So this is the importance of and transmission and distribution also. And in transmission, even in transmission systems, the overhead transmission systems occupy a lot of space. So due to increased awareness of farmers and demands on right of way, so the land is becoming costly, and even farmers are not willing to give their land for transmission network. So this is another problem where right-of-way demands are gaining momentum. And apart from this, we can see on the right side, we have wind farms and solar farms. These are renewable energy sources. And for integration of renewable energy sources, which are in remote place normally, we do need a cable transmission. So for long distance transmission, we prefer underground cables, and even for offshore wind farms, we do need submarine cables. So these, due to these demands also, power cables are gaining importance. And apart from these, you can see the problems associated with overhead transmission systems. So here, a line crossing through forests or trees, so what are expected faults, interruptions, etc. are expected, and growth of plants even is also affected by the transmission lines. And you can see on the right side, branches of tree falling on the transmission line that may lead to interruption or fault. And even for the safety of human beings, you can see when a tree is touching a transmission line, actually the voltage profile in this red region is almost same as the transmission line voltage. So you can expect the fatality to any human being touching the tree when such a case arises. And the voltage actually reduces to zero around 10 meters for a 60 kilovolts line. So you can imagine how much effect this kind of trees touching the transmission line would result. Apart from fault, they may also cause damage to life also. So apart from human beings, you can see many animals getting electrocuted on transmission lines. So these are all reasons, even birds sitting on transmission line, when they touch both the lines, they get electrocuted. So like this, there are several disadvantages with overhead transmission systems. Therefore, the alternate is, power cables, and overhead cables, overhead covered conductors are also alternatives for this kind of situations. Voltage and electric fields. The purpose of a wire or cable is to convey the electric current to the intended device or location, it is important to keep the current from flowing in unintended paths. So electrical insulation, dielectric is mainly provided to isolate the conductor from other paths. So conductor conveying electric signals or power is an insulated conductor. So this is about the introduction. And you can see electric fields and voltages on overhead conductors. Here actually method of images is used here. So this is the ground actually, the central plane, whatever is shown is the ground. And here the conductor is there. And then the electric field lines you can see here. And then these are the equipotential lines. So this is how electric field distribution will be there for a transmission line conductor. Of course, the bottom portion will not be there. But for solving this problem, we use method of images. So instead of using a ground plane, we replace the ground plane by an image of the conductor exactly symmetrical to the ground plane. Here, a negative charge. This is an image of this charge, and then this will be useful for solving the electric fields in overhead transmission lines. So an air insulated conductor, actually overhead conductor is also an insulated conductor where air is used as insulation. It is actually widely used, but if space is not a constraint and a large resistance exists between the conductor and ground, lower voltage breakdown strength than many other insulating materials, of course, since air is the only insulation. So all other solid or liquid dielectrics have higher breakdown strength than the air, so it is lesser insulation only. Corona represents power loss and can cause interference to radio, TV and other signals. These are the disadvantages, of course. The breakdown strength does not increase proportionately as the thickness increases. So this is another disadvantage of this one. Apart from the problems we have seen just now, using overhead bare overhead conductors without solid insulation. So electrocution, etc., safety, and then faults, so interruptions, all these problems are associated with overhead conductors. Therefore, we use covered conductor insulating to save space. Covered conductors means, there are several types, even cable is also a covered conductor. Covered conductor need not essentially be a cable. So here you can see the central electrode or central conductor, maybe an overhead conductor. Surrounding that there is an insulation. So if the insulation is again surrounded by a semiconducting layer or conducting layer, then it is called a cable. But if that is not so, it is simply called covered conductor. So in case of covered conductor, so there will not be, when we mention covered conductor, there will not be any layer surrounding the cable. Layer means any conducting layer. Only insulating layer will be there. So this is the conductor, and some portion of the air gets replaced by better insulation here. And voltage from the surface to covering to the ground is this is the potential difference. And one advantage of covered conductor is the covered conductor, the voltage drop when no one is touching, or when no plant or nothing is touching the surface, then the voltage drop will be just 5%. Means whatever is the conductor voltage, just 5% drop means around 95% of the voltage will be there on the surface. But whenever a tree or any conducting object touches the surface potential will become zero, or where the potential at which it is touching. Of course, the object which is touching should be at ground potential. So in that case, the potential of the touching point becomes zero, entire voltage drop will be inside the covering only. So that way it doesn't damage any, it is not fatal to any living being, or it doesn't cause any fault when touched upon by these trees. It is distinct from overhead conductor. So in terms of safety as well as reliability. Reliability means continuity of power supply is concerned. So the outer surface of the covering has a voltage that is within a few percent of the voltage on the conductor. In fact, we have reported this recently. And designs involving 2 or more layers are commonly used in low voltage cable designs. So often 2 or more layers of insulation will be used. And the outer layer serves both as insulation and jacket, as it needs to be tough also, sunlight resistant also, and flame resistant and chemical resistance, because it will be facing the weather. Now, electric field inside the cable dielectric, this is under AC conditions. So electric field E in cylindrical geometry is given by rho L by 2 pi epsilon R. Rho L is the charge density on the inner conductor, linear charge density. And voltage is given by this condition. So if you substitute, then electric field will become V by R into ln R by R. So if we plot the electric field, it will look like this. It will be decreasing from the conductor to the outer boundary. Of course, inside the conductor, there will be no electric field. This is insulation. And the grounded sheath again is at ground potential. There will be no electric field inside the grounded sheath also. So this is how electric field will vary in AC cable. And in AC cable, the electric field is not dependent upon temperature, etc. Of course, a little bit dependence will be there. But in DC cable, the dependence is more, and then electric field changes dynamically. So here, in case of AC cable, the electric field is high at the conductor boundary and low at the sheath boundary, grounded sheath boundary. But the reverse can happen in case of DC cables. Under loaded conditions, the electric field will be low at conductor and high at sheath. This may happen in DC cables. So AC cables, it is like this only. It is more or less independent of temperature. So the solutions for overhead transmission, alternate solutions are given here. So different types of cables are given here. This is a single sheath covered conductor. You can see just inside one conductor and above that one insulation layer. So there is nothing above or below this one. And here the second one is high voltage covered conductor. You can see several layers here. This is inner conductor. Above that there is a inner semicon layer and outer semicon layer. So in between there is a insulation, number 3. So why these semicon layers are used, we will see soon. So this is a 3-layer cable actually. Of course, the conductor is at the center. 3 layers corresponding to which do not relate to conductor. One is inner semicon, outer semicon, and in between there is an insulation. So this is another concept known as spacer cables. Here you can see 3 cables are separated by a spacer arrangement, rigid spacer arrangement on a pole, which is actually a wooden pole. So there is a messenger wire here for mechanical support here, and then this is known as tangent bracket, and 3-layer cable of 3 different phases here. So this is known as spacer cable. So this is used for overhead purposes only. Of course, this is also overhead cable only, overhead covered conductor. And here, this is a universal cable. Universal cable means it can be used for underground also, overhead also, so without any problem. So in this case, we have, of course, this is very costly arrangement, very costly. But we need not have any terminations, cable terminations, and we need not have any change in, impedance. So surge impedance, if you have continuously one cable system, so the network is uniform. Otherwise, if you have, from cable to overhead to cable, transmission systems, then the surge impedance is different at interfaces, so which causes traveling waves actually. So these are several overhead covered conductors, and with the universal cable here it is given. Apart from these, underground cables also will be used. So there are several types of high voltage cables are there, underground and submarine cables based on location. And based on voltage and current, they can be divided into AC cables and DC cables. And based on insulation materials, they can be classified into mass impregnated cables, oil-filled cables, and polymeric or extruded dielectric cables. So among these, the polymeric and extruded dielectric cables are latest cables, latest technology. Mass impregnated or oil-filled technology is old cable technology, but which was very successful in the sense until very high voltages, even 800 kilovolts, the technology is proven to be working. Polymeric cables, recently the 525 kV, up to 525 kV, the cables have been developed and tested, but installation is much below that voltage level. So these are the several types of extruded cables. Here, typical structure is given here. So there is a central copper conductor you can see, and immediately after copper conductor, there is a small semiconducting layer, black color you can see here. So this semiconducting layer is known as conductor shield. Actually, why this kind of semiconductor shield? Above the conductor, we use another semiconductor shield. And above that only, this insulation layer will come. This is the insulation layer. Here it is indicated as XLPE, tree-retardant XLPE, or ethylene propylene rubber insulation. It can be any of these. All these are called extruded dielectrics. And above this cable, above this insulation material, there is an insulation shield again, which is again, conducting material, semi-conducting material. So this is kept above this insulation layer. And above that insulation shield, again copper tape is seen here. And above that, then lead alloy sheath is used here. So this lead alloy sheath is for preventing the moisture from entering into the insulation. So, and then above that polyethylene or PVC jacket you can see here, above that. And above this again, metal wire armoring. Of course, there are several types of armors that we will see later. So there is an armoring, so which will protect the cable from mechanical wear and tear. And even above that, there is a covering actually for the cable. So you can see so many layers of a real high voltage cable. So much care we have to take because it is very, very, very important for a reliable transmission system. Because failure of cable is, failure of power systems. That's it. And the repair involves not only money but also time, which causes huge losses to power systems and inconvenience to the customers also. So this is about extruded cable structure, typical structure. So of course there will be slight changes in the structure. Different companies use different layers and different structures, but more or less this is the general or typical structure of a extruded cable system. And apart from this, mass impregnated cable system is here given here. So of course, conductors can be aluminum or copper. We will see later how conductors are selected. And there is a semiconducting paper tapes are here. So unlike extruded insulation where, we have extruded material as a semiconducting layer, here semiconducting paper tapes are used inside as shielding. And above that, insulation made up of special pulp high density paper impregnated with high viscosity compound. Again, it is high viscosity oil only. So that will be impregnated into the paper. This is actually made up of paper insulation. So several paper layers are wound to form the insulation. And above that again semiconducting tape will be there. And above that again lead alloy sheath, again polyethylene sheath, and then steel tape reinforcement and bedding, and a double layer of high tensile flat steel wires. And here you can see armor, and above the armor again polypropylene yarn outer survey. So this is the typical structure of a mass impregnated cable. It is also one of the successful cables. Until 500 kilovolts, it served without any problem under AC conditions. So even for DC also it has been used in the past, but it is a old cable technology now being replaced by extruded dielectrics. And this is another oil-filled cable system. Here it is more or less similar to mass impregnated cable only, but here instead of high viscosity oil, low viscosity oil is used, and there will be a central duct in the conductor itself. So where this is oil can flow here, this is oil duct, and then this is again paper insulation only. So this oil is maintained under pressure at both ends. So we need to have pressure maintaining system where oil pressure is maintained. So this system has involves additional cost, but it can go up to 800 kilovolts without any problem. But length is limited. Length of the cable is limited, unlike mass impregnated cable case, because you have to maintain the oil under pressure over a long distances. So that is the limitation of this one. This is also old technology, but still it is proven up to higher voltages. So among the three cases shown here, this is highest voltage. This can tolerate highest voltages, or designs are available for this under high voltages. And mass impregnated is next, and then next is polyethylene based or extruded dielectric materials or extruded cables. Of course, the extruded cables are having additional advantages because ease of making them, manufacturing them very easy, and then repair is also very easy. In case of repair, in case of cable breakdown, we need not worry about oil spilling over in the sea or on the floor, and need not fill up oil again. So that kind of problems will not be there for this extruded dielectric cable, and easy to cut and then repair. So this has several advantages. That is why the technology is gaining momentum. And almost all modern cables are polyethylene based or cross-linked polyethylene based insulation systems or cable systems. Now among the cables, again AC cable or DC cable, which is good. Actually cable is a cylindrical capacitor. So if we connect a cable to a source, even if there is no load, cable itself will draw leading reactive current. So if the length exceeds a certain distance, this is under AC I am telling about. So if the cable length extends a certain length, beyond that the current of the cable, the reactive current of the cable drawn by the cable may exceed the rated current of the cable itself. So therefore, there is a limitation of length on AC cable. So unless you supply with reactive power in intervals, in certain intervals of cable length, we cannot use the AC cable for longer lengths. That is the basic limitation of an AC cable. But do you expect the same in DC cable case?
No, sir, because there is the charging current can only happen between the interval of 0 and charging.
Yeah. So the transient current only during the switching, there will be a transient current, but normally under DC, once it is charged to full voltage, we don't expect any reactive current like this. So DC has this advantage. So for long distances, of course, beyond the practical distances are around 60 kilometers. So beyond 60 kilometers, DC cable is preferred. So therefore, in European countries where islands are separated by a sea, so long distance submarine cables are to be used. So there where if it is more than 60 kilometers, they must go for DC. Therefore, back-to-back DC connections are more in European countries. So even in our country, DC has additional advantage such as asynchronous connection between the networks, and increases the stability of the system. So therefore, DC cable transmission is again gaining momentum over the AC cable systems. Now, in the cable systems, we have just seen the structure of the cable. So what are the importance of sheaths, jackets, and armors? So that we can see, because apart from insulation layer, there are sheaths, there is a jacket, and then armors are used. So what are these? So review of fundamentals of shielding. Shielding, this conductor shielding, where a small layer of a semiconducting layer is laid over the conductor. So you can see conductor is having several strands. So wherever there is sharp curvature, you can expect high electric field here. So to make the electric field distribution uniform, we put this conductor shield, which is also conducting actually. Of course, it is made up of polyethylene material only in case of XLPE, but in which carbon compound is mixed so that to make it a conductor. And that layer is smoothly laid over this copper conductor so that the outer surface will be very smooth and which eliminates the electric field enhancement due to sharp curvature. So now the curvature is smooth, therefore electric field will be uniform across the entire perimeter of that one. So symmetrical radial stress distribution, and which eliminates the tracking and other surface effects. So if the conductor is not smooth, so wherever the small radius of curvature is there high electric field will be there, which will cause cracking inside the insulation material, and then ultimately it will break the electric cable. And exclude outer covering, tapes, sheaths, jackets, etc. from electric field. And there is, you can see here, outer insulation shield it is called. The lower semicon layer is called conductor shield because it is shielding the conductor. But similarly, we have one more layer of semicon layer outside the insulation, XLP insulation, which is called insulation shield. So the purpose of this is to exclude the outer covering, tapes, sheaths, and jackets from electric field. So we don't want electric field to come out of this insulation shield. There itself we will, so entire electric field will be inside the dielectric medium only. And outside, when there is a conducting medium, obviously it becomes zero. So we don't want the electric field to be outside. So that's why the outside means the copper tape or other jacket, etc. are outside. For that, we don't want electric field outside. That's not, this material is not for, protecting electrical, in electrical way. This is for mechanical protection of the cable. So we should not subject this to electric field and damage it. So that's why we put this insulation shield here. And uniform surge impedance and effects of induced direct over voltages will be minimized. So if you make this insulation shield and conductor shield, which make the outer surface and inner surface smooth, so you can expect the surge impedance. Surge impedance is impedance seen in transient conditions between this copper conductor and outer insulation shield. So that becomes uniform if the layers are uniform. See, inner layer and outer layer are uniform. If they are not uniform, say for example having the a structure like this, non-uniform structure in which a lot of sharp points are there or sharp curvature is there. So in that case, you cannot expect a uniform surge impedance. So this also helps in having the uniform surge impedance all along the cable length. So these are the fundamentals of shielding, and then jackets and covering. So as part of covering, we have metallic covering also, which is called sheath, non-metallic covering, which is called jacket. You can see once more. So here you can see lead alloy sheath. This is metallic sheath. And here you can see polyethylene or PVC jacket. So this is called jacket. And above that armor you can see. So sheath is used as a barrier against moisture ingress. So lead sheath, the metallic sheath, is used as a barrier against moisture ingress into the cable. Moisture is actually very detrimental to cables. It will cause breakdown of cables very easily. Even few percent of the moisture can destroy the insulation. That's why the cables, high voltage cables, are hermetically sealed in lead tubes. This what is lead sheath it is called. So here you can see this is a lead tube, metallic tube. So cable is completely sealed within this tube. So in order to prevent the moisture from going inside. So the metallic sheath is used as a barrier against moisture ingress, and jacket is used for mechanical protection. So this jacket is used for PVC or PA jacket is used for mechanical protection. And there are among the jackets, two types of jackets are there, thermoplastic and thermosetting. So curing process reversible for thermoplastics means, you can heat it and melt it and then bring it back to the original shape. And curing process is permanent for thermosetting jackets. Thermosetting jackets, once they are fixed into a shape, after curing process, you cannot melt them and then make them back again. So material cannot be recycled. But we do need such a systems where there is, high temperature systems or, robust systems are needed. For example, thermoplastic jackets are used in underground cables, PVC, polyethylene, polypropylene, etc. are used. Thermosetting jackets are used in industrial or power plant cables, where, we need a robust system. So if it melts and then becomes liquid, it no longer protects the cable. So such things are not expected here in power plants, etc. So XLPE, neoprene, and then CSP, nitrile rubber, etc. are used as thermosetting jackets. And as per the armors, there are again two types of armors are there. Here interlocked armor you can see, and here round wire armor you can see. This is a round wire armor, and this is interlocked armor. So these kind of systems are used in aeroplanes, where light weight is expected. Not only that, also for measuring cables, where we have to completely seal the signal cable. Of course, I'm talking about a signal cable which is of very low voltage, but the system is same. That's why just I'm recalling here. So here similar sealing will be there, which will act as electromagnetic shield, so which will not allow any external interference to the signal cable. So such kind of interlocked armor, aluminum armor are used in signal cables also. Also in aircrafts, such a system is used because it is lightweight. And then such kind of round wire armors are used in underground and undersea cables, which have, of course, high tensile strength also. Now, among the conductors, just 1 minute.
Sure, sir. Sure, sir. Sure, sir.
No. Yeah, I'm busy. I'm in electric. Okay. So, conductors. In conductor selection of materials, we need high conductivity. Ampacity means current carrying capacity. Weight, low weight, high thermal stability, the abundance of material, availability of material, and low cost, resistance to environmental conditions. So these are the factors that will govern the selection of a conductor material. So it depends on country to country also, because somewhere in some country copper is abundant, we'll use copper. So of course there are differences in the material properties. As per tensile strength, copper is having more than aluminum. Tensile strength for same conductivity is of course same. Weight for same conductivity. So here it is 100 and it is 50 for aluminum is lightweight. And cross section for more conductivity. Of course aluminum you need more cross section. And then specific resistance, aluminum is high and copper is low. So losses are low in case of copper. And coefficient of expansion, thermal expansion, is more, aluminum is having more. So based on the properties, of course, we have to change, tweak into the design a little bit, but any material can be used, aluminum or copper. So only for the differences in design, more or less, they do not have any distinction of usage. So both are frequently used for power cable transmission. And conductor selection size, how to decide the size. So size is decided based on rated current capacity at rated voltage and short circuit capacity, voltage regulation. Of course, if resistance is more, you expect more voltage drop. And ampacity, considering external factors such as soil thermal resistivity. Ampacity means, current carrying capability. So how much current it can carry without rising a temperature to beyond certain limits. And effective resistance, what is AC resistance and DC resistance, and what is the ratio of AC to DC resistance. So these will govern the selection of conductor size. And we have standard sizes, of course. So this is American wire gauge, one of the commonly used conventions for conductor sizes. 0000 AWG means 0.46 inches. And the ratio of any diameter size to the next smaller size is given by this quantity, 0.4600, 0.0050 under 39th root. So which is equal to 1.122932. So sizes are governed by this ratio, standard sizes. So short circuit rating for 1 second duration for copper and aluminum XLP cables is given in this table as per IS 7098 part 2 1985 standards. So here IT is the short circuit rating for T seconds, which is equal to ISH by root T, where ISH is a short circuit rating for 1 second and T is the duration in seconds. So if T increases, the current rating is decreasing here, you can see. And maximum conductor temperature during operation, normal operation, means without any problem when supplying the required load current, maximum load current. So maximum operating conductor temperature is 90 degrees centigrade, and maximum conductor temperature during short circuit. So it is for 1 second duration, it is 250 degrees centigrade, up to 250 degrees centigrade it can go. So beyond that, if it goes, then you have to change the load or voltage level, etc., or change the design of the conductor. Now conductor resistance, the skin effect and proximity effect. Here skin effect is given. For AC cases, this skin effect is frequency dependent actually. You can see the skin depth is given by this formula, delta, so which is given here. So what is skin effect? The redistribution of alternating current within a conductor leading to an increase in the effective conductor resistance. So within the skin depth, actually most of the part of the current will flow. So inside very less current will flow, which will cause non-uniform distribution of current, which will increase the resistivity or resistance of the conductor. So this happens in AC case only. And similarly, proximity effect. So here, when the two conductors are adjacent to each other, and when they are having, opposite current, the current at the outer surfaces will be high, and when they are having similar currents, the current density at the inner surfaces will be high of the conductors. So this is another effect which causes the non-uniform distribution of the current and ultimately causes the resistance to increase. So these need to be considered in designing the currents of conductors. And the need for a stranding of the cables. Can't we use a single solid conductor? So we cannot use for several reasons actually. A solid conductor develops considerable amount of internal stress during bending, and it is not flexible enough. You cannot bend the cable actually. So therefore, solid conductors are not used, and they are also more prone to effects of skin effect and proximity effect. During termination and jointing, solid conductors suffer from a high contact resistance. Because only single conductor is to be joined, it will have high contact resistance. Overall contact resistance will be high. So that is another problem with solid conductors. Therefore, there is a need for stranding. And with stranding, actually, the cable is not actually straight. Means, the length of the cable, actual cable length, actual wire length is more than actually lay length. Lay length means actually whatever it is used for, the physical length of the cable. Because it has to be wound around a central conductor, and then that's why the overall length increases. So there is a concept of lay angle of the stranded wire. So you can see this is a strand. So the perpendicular distance between these layers is d, and the width of the conductor is d. Then sin alpha is equal to d by d dash, where alpha is known as twist angle between the axis of the twisted wire to the perpendicular plane of the axis. So this is also known as lay angle, which is here, for particular case it is given as shown as alpha is equal to around 72 degrees and 46 minutes. So this angle is known as lay angle. It is useful for several calculations. I will show you. And forces in stranded conductors. So it is not straight. You can see a kind of helical structure like this will be there over a length of the cable. So several forces will occur here. The bending forces get compensated due to the geometry of the stranded conductor. But in case of aluminum strands, there is an additional decrease in the effective resistance of the conductor. So as per the forces during the stranding, a torsional force acts on the conductor as the axis of each wire rotates on a helical path, as can be seen here. And what is that torsional force is given in the next slide. So this is the torsional force that is experienced by the wire, which is 2 pi sin phi, where phi is the lead angle of the helix. And increment in the length. So as just now pointed out, the actual length and lay length of the cable are different, or wire are different. So due to stranding of wire, actual length requires more than the center wire. So the increment in length is given by L minus H, where H is the lay length, L is the actual length. So H by sin alpha minus H, which is equal to this. You can sin alpha is always less than 1. You can this quantity is more than 1. So always we will have certain value for L minus H. So this is increment in length due to stranding. The fundamentals of stranding we will see after a few slides. So due to stranding of wires, there is of course an increment in area also, which can be calculated using this formula. There are multiple layers of stranding. So there are several layers of stranding actually, not only single layer of stranding. There is a central wire, and above that one layer of stranded wires, and above that another layer of stranded wires. Mostly they are alternated like this. One is right-handed lay, another is left-handed lay, so that there will be less chances to open out and very tight, and then prevent bird caging action. You can see this is bird caging action. So this is how wires will come out. So if they are opposite like this, different layers are opposite like this, then it will prevent these kind of things. And during armoring also, it helps keep the conductor in a tight position. Now this gives a description of various conductors in various applications for domestic buildings, for mining cables, for cranes, mobile equipment, and then railways, locomotives. So for signal and control cables, instrumentation cables, etc. So you may refer whenever you want these. And these are the typical types of conductors used in transmission line. I'll go through quickly these ACSR and ACR, all you may be knowing. And this is a filling factor. Filling factor is area of metal content into 100 divided by geometrical area of the stranded conductors. So total area n into pi d square by 4 divided by pi d square by 4. This is the filling factor, a quantity which is less than 1. So close to 1 means, it is 100%. There is no empty spaces. You can see here compact cables, which is compacted by minimizing the gaps here. So these have lower power loss can be achieved here, and size also gets reduced due to compactness here. Now, how many strands can we put surrounding a central conductor? Anyone? Suppose the diameter of all the conductors is same. Will it be a fixed quantity or something different?
I think it should be a fixed quantity.
Yeah, it is a fixed quantity only. Actually, you can show theoretically that the number of strands surrounding a central conductor is 6. And it will be in this sequence actually, 1 plus 6 plus next layer will be 12 plus 18 like this. It's also called kissing number because exactly 6 will fit here, surrounding a central conductor, if the diameter is same. Of course, same diameter strands only will be used. So this how several strands are wound around the cable, a central conductor. And there are here certain problems with round conductors. You can see these 2-core round conductor, this is 3-core round conductor, this is 4-core round conductor. What are these small circles here? Apart from these 2 big circles, we have these 2 circles also. These are actually not cables, these are actually not wires actually, they are filling material. Of course, they are made with plastic also, so or even jute also. So these need to be filled, otherwise the strands will move freely. So in order to prevent that, this large space, jute fillings are to be used. So the disadvantages with these round conductors is a large space, jute fillings will cause extra weight, increase in laid up diameter. Transportation, installation and packing and jointing also costs here in this case. But we have, so this has resulted in designing a different conductors here, sector shaped conductors. You can see the conductor is divided into 3 sectors here. So this is 1, this is 2, this is 3 sectors. But the shape you can see, these are like, a circle is divided into 3 parts. So what are the effects? Let us see how far we can go, how high voltage we can go. And this is elliptical shaped conductor, you can see. These are the advantages, disadvantages of various types of conductors. Low radius of curvature. Here there are sharp curvature here at these 3 corners you can see. Here. So low radius of curvature, high peak electric field concentration. Therefore, electric field is inversely proportional to radius of curvature. Wherever radius of curvature is small, the electric field will be high. So here in these three corners, the electric field is expected to be high. And low dielectric strength, because the electric field is high, then the failure will occur at lower voltages only. So low thermal withstand capability, because all three cables have to be here, and then heat escaping will be difficult here. So therefore, the voltage ratings of such cables with such conductors is around 6 to 11 kilovolts only. And next is elliptical shaped conductors, which have a medium radius of curvature, less peak electric field compared to this one, and higher dielectric strength compared to this one, higher thermal withstand capability, and used up to 33 to 66 kilovolts. And for this case, round conductor case, it is up to 66 kilovolts, it can be used, and the radius of curvature is high, therefore electric field is low. So we will see for sector shaped conductors how the electric field will be enhanced at several corners. So this is a typical cross section of a sector shaped conductor. You can see here, this is the sector shape. So here, this is one sharp edge, this is another sharp edge, this is another sharp edge, this is another sharp edge. So the electric fields at different positions is given here. This is EA, this is EM here, and this is EN. Of course, these are complicated derivations, but already available in the literature. So one can use these in designing the maximum fields and voltage level or insulation thickness required to meet the voltage level. So these calculations are useful. And electrical properties of insulation materials per cable is the next topic here. What are the fundamental properties that are of the insulation that are important? Here, volume resistivity. Of course, ideal insulators are expected to have infinite resistance, but there are no ideal insulators, ideal dielectric materials available. So every material, all commercial materials will have finite volume resistivity. Of course, very high, 10 to the power of 11 to 10 to the power of 15 level. So in ohm centimeter it is measured. But of course, that will give us an idea about the quality of the insulation. So greater the resistance, better the ability of the polymer to serve in electrical insulation. Units are ohm centimeter, these standard units, and useful for estimating the condition of the cables. So, volume resistivity, rho, is resistance into area of the electrodes by thickness. So this is how between two electrodes the dielectric material is placed. Of course, we use a 3-terminal electrode with a guard electrode actually. Here guard electrode is not given, of course, but this just gives the concept how volume resistivity is measured. So volume resistivity in fact is an important property of cable dielectrics, which is useful for assessing the cables. And next is polarization. So what is polarization? When we apply certain voltage, these dipoles tend to rotate and align themselves in the direction of electric field. So here you can see what these dipoles, in terms of polymeric chains. So this kind of phenomena may happen. Here when there is no voltage, the polymer chain you can see side chains are in arbitrary direction. But when voltage stress is applied, the polymer chains will align themselves in the direction of electric field, because these polymer chains will have along them positive to negative or negative to positive polarity. So behave like dipoles. So they align in the direction of electric field. And in another case, this is a polymer chain with certain polarity. This is with another kind of structured charge structure. So when electric field is applied, they move apart like this. So as a net result, you can see when there is no electric field, the polymer structure may be like this typically, and then when electric field is applied, they tend to align in the direction of electric field. So what will happen when the dielectric is polarized compared to it is when there is no polarization? What
The
is
net
that?
electric field will reduce.
Net electric field
Inside
will
the
reduce.
dielectric.
It's not actually net electric field. Net electric field, if it gets reduced, then how integral E dot dr will become voltage?
I meant the region between the dielectric. Due to polarization, we will have a reduce in the electric field because the electric field, internal electric field of the dipoles, they will be opposite to the direction of the applied electric field.
Okay, so the internal electric field will oppose the main electric field. It tends to reduce the main electric field. But what will happen ultimately if the net electric field really gets reduced, we cannot meet that integral E dot dr is equal to V. So the resultant electric field should not change for a given applied voltage. So what will happen in order to, when the dipoles tend to reduce the net electric field, what happens is the electrodes will get additional charge and compensate the loss in electric field. So this additional charge will create additional electric field, and then the overall electric field will not change. So that's how we get additional charge storage capability due to this polarization. So the polarization results in additional charge accumulation on the in the electrodes for a given voltage. And the dielectric constant. So dielectric constant is a measure of the ability of the insulation materials to store electrical energy, of course charge. The ratio of charge stored in the polymer as compared with that in a vacuum is given by this dielectric constant. Of course, it has no units, it's a pure number, and K is normally greater than 1 for non-conducting or insulating materials. So we'll see different dielectric materials having different dielectric constant. Of course, as long as epsilon is constant for us, then the electric field inside the medium is independent of epsilon if it is constant. Of course, the epsilon, if it changes, or K, if it changes with electric field or temperature, then the field distribution is non-uniform and it complicates the field distribution and may cause enhancement in the field. So here you can see polyethylene. Hello?
Yeah, you are audible, sir.
Okay. So here power has gone, it seems. Okay, no problem. My laptop is on. So these are different materials whose dielectric constant is given here. You can have this for your reference. And dielectric losses. So dissipation factor, so which is a factor which gives us the information on the efficiency of the insulation. So loss of energy due to sinusoidally varying applied field due to polarization, of course. So if alternating electric field is applied, these dipoles tend to align and de-align in the direction of electric field. Then how losses will occur?
When there is alignment and de-alignment, we will have some sort of friction between the poles. So thereby small losses will be contributed by each dipole. So totally they will sum up to a huge loss. I mean, totally they will sum up to the total loss.
Actually, it is not the friction. So when a dipole rotates in an electric field like this, then it radiates the energy. So due to this radiation, the radiation itself is absorbed by the material again in the form of heat. It is dissipated finally. So due to this alignment and de-alignment or rotation of the dipoles, the electromagnetic energy gets radiated into the environment. So that radiated electromagnetic energy is itself absorbed by the material before it escapes actually, and then dissipated in the material. So due to this alignment and de-alignment, the losses will occur. But how long these losses will occur? Can we, if we increase the frequency, the losses will continue to increase. What will happen after certain frequency? The dipoles stop responding to this because the speed is so much, they cannot respond to the external frequency, external voltage. So where the losses again tend to decrease. So this is the typical characteristic we observe with frequency. So of course we are interested in power frequency, which is small, where dielectric dipoles respond to the frequency, and the losses will be there. This dissipation factor or losses or tan delta, what it is called, will indicate how efficient the insulation material is, or how much good the material is. And the insulation responds to high stresses. So this is actually very important phenomena in power cables. So in power cables, so the insulation is actually more susceptible to failure. Breakdown of insulation takes place as applied voltage is more than the dielectric strength of the insulation. Of course, that is original strength of the insulation. But in practice, what happens? Electrical and water treeing takes place under high stresses. So this is very important for polyethylene cables or extruded dielectric cables in general, because they are the modern cables. That is the latest technology, and still the technology is yet to be proven for higher voltages. So a lot of investigation is still going on, development is going on, and people are trying with nano materials, and then with new materials, of course, without fillers also some people are trying. So this ultimately the purpose is to prevent the failure of the insulation and increase the voltage level of the cables, of extruded cables. So they are limited to use below 500 kV till date, and our power system voltages are increasing beyond even 1200 kV. So we are yet to develop these extruded cables to that level. So these important phenomena, two important phenomena that occur in the insulation are very, very important to be addressed. So those are water trees and electrical trees. For water tree, water is required. There are two types, fan and bush-shaped trees will grow and grow for years together, and microvites connected by tracks of oxidized polymer will cause this kind of water trees. And electrical trees, water is not required. They will occur even inside the insulation. These will occur, water trees will occur mostly at the outer boundaries and sometimes inside also. And for electrical trees, water is not required. Needle or spindle shaped, they look like, and failure shortly after formation of carbonized regions. But in this case of water trees, failure will take longer time. But electrical trees are faster to result in a breakdown compared to water trees. So you can see the images here of electrical treeing. So here there is a contamination you can see. So surrounding the contamination, you can see the damage, and here a breakdown channel. And since these look like tree branches or tree roots, whatever it is, so these are called trees. So here also, this is in case of cable. Here you can see this is cable dielectric. This is outer sheath. This is inner sheath. Here you can see the several strands also. So three, 4 strands are visible here. And over the strands there is a semiconducting layer, so which will smoothen the electric field here on the surface. But you can see from the outer surface, this kind of treeing structures have come into picture, come into existence. Actually, water trees are not visible to the naked eye. They have to be dipped into a dye so that the dye fills the tree channels and then becomes visible. There, in this case, some blue color dye is filled, and then you can see the water trees here. So they have come from the outer surface, you can see, from some places, and then entered into the insulation. And over a period of time, they joined the two insulating, two layers of conducting layers. So this will result in ultimately breakdown here. So this is the electrical tree. This is typical water tree shown here. Let us go into the details. These are various trees here shown here. So water treeing, again, this is water tree. So what is a water tree? It is one of the pre-breakdown phenomena observed in power cables, of course. Water tree refers to the formation of minute paths in a dielectric along which water penetrates under the influence of a high electric field. Water or moisture penetrates into under the influence of a very high electric field. But upon removal of moisture and voltage gradients, they disappear temporarily. However, the nature of damage is permanent, as again if the restoration of conditions, again it reappears. So therefore, that the damage is permanent only. They may disappear or not visible if you remove the voltage gradient, but the damage is permanent. So these penetrate into the dielectric under the influence of high electric field with in the presence of water. The structure looks like this bouquet shape are formed as a result of alignment of these cavities in contrast to the branches of electrical trees. Electrical tree, just like lightning you have observed, na? So it will be like that. Tree branches will emerge from that. Here, water tree looks like a bouquet. Just wait. So here it shows density of bouquets versus distance measured from a needle tip. So for experimental purpose, we use needles to investigate such kind of tree structure, formation of such tree structures. So, and then structure of water trees. So under high power magnification, water trees may be seen as discrete ellipsoids like this, ellipsoid shape, which tend to line up in the direction of the electric field lines. And the insulation between these ellipsoids may be deteriorated through oxidation or other means, but they remain as adequate electrical insulation for a long duration. So unlike electric tree, which is very fast, so this takes longer time even to break down. So the formation is shown here, which looks in the ellipsoids, and in between the insulation gets deteriorated very slowly, and after a long time it will form a channel, of course. These are several types of water trees. You can see this is from inner semicon, how the trees are getting originated inside the insulation, you can see. This is again from inner semicon layer. This is from outer semicon layer. And another tree is, this is bow ties. Looks like bow tie, that's why it is named like this. Trees growing from voids or contaminants inside the cable insulation. So sometimes water trees grow inside also, where there is a presence of some void with some moisture.
Sir, but how can water trees originate from the inside of the conductor?
Sometimes some voids will have accumulated, moisture with them. So only in that case it can originate like this.
Okay, sir.
These are more frequent. This outer surface and inner surface more frequent. Of course, to prevent these, we will of course take the precautions by filling the conductor. Conductor, there are some small spaces. So there will be certain material which will be filled even in that spaces to prevent the moisture ingression through the conductor side also. And as well as the cable itself is sealed in a lead tube. But irrespective of that, whenever we open for repair, etc., for a temporary period, even during that, moisture will enter into the insulation. So over a period of time, that may result in breakdown.
Sir, how can we identify this kind of happening inside the cable? How can we measure, identify such kind of happening inside the cable?
You mean online identification or?
Yeah, because this is a cable and that is a underground cable, maybe somewhere. How we identify somewhere problem like this tree formation?
It is not possible. Till date, we do not have, online condition monitoring techniques for a cable. Actually, there is a lot of scope for research in power cables. Even fault identification, even the weak portion identification or aging identification, which require online because the cable is buried inside the soil. So if we can guess exactly where the problem is coming, then we may even decrease the load in that cable, or we may take preventive measures or make alternate routes ready. So this is possible, but of course the techniques for identification of such problems are not available now. Only after breakdown we can analyze and then tell that this is what happened there. So before breakdown, if we can tell, that is a great opportunity actually. People are, even our lab also, 2 students are working on that, but it is a long way to go. Because
Sir, one small question, sir. Balaji here again.
yeah.
So, by leakage current measurement through the sheets, cannot that be indirectly correlated?
Leakage current, see, if it is a local phenomena, if you measure locally, you can say something about it. But over a length of the cable, where do you measure the leakage current? Complete leakage current picture will be there. So leakage current of entire cable, if you measure, nothing can be deciphered from that. Okay.
Okay, sir.
So that's the problem. So if locally, if you are doing in a laboratory on a sheet of sample, and then in that water tree you are growing, then you can say, this is the characteristic of what leakage current when a electric tree grows. But in entire length of the cable, if we were to say something at particular distance, some problem is occurring. So that is difficult. It's not possible. As of now, it is not possible. Of course, by understanding the leakage current in local experiment and correlate that to with the distance, whatever you are measuring at a remote location, and if you can correlate somehow by some calculation that at a particular distance this is happening, then that is a great achievement, of course. So a lot of research is expected in this, because failure of a cable is a huge loss. And you can imagine, of course, now the technique of finding the location where the cable failure occurred is available within certain meters precision. That means you can dig a few meters and can find out where exactly it has failed. That technique is available. Of course, even in that also there is a lot of scope for improvement. Precise location, finding precise location is very important, because you need not dig half a kilometer of the cable and then find out. If you can tell exactly where the failure occurred, so with a few meters or with 1 or 2 meters precision, then what will happen? The loss will be reduced to a large extent. For example, for 1 feet digging in Bombay, one of the company told they have to pay to the municipality, just pay, not for the digging cost, etc. They have to pay to the municipality ₹1 lakh in Bombay city. So you can imagine if the failure occurs in a city and we have to dig for half a kilometer, so to find out the failure. So a lot of scope for research is there in cables, and it is an upcoming area, and all future transmission and distribution has to be through underground or submarine cables only, because the growing awareness of the public, even rural area, they don't like to have transmission lines over their lands, and they don't like to give the land to transmission or distribution companies, and they are becoming private companies. Of course, if it is government, they can take forcefully by making a law, but if it is for a private company, a lot of agitations may be there. So this is the case. Yeah. Now let us see the phases of water tree. It has inception, growth, propagation, and breakdown. So ultimately final is breakdown. Initially it starts with inception. For inception, certain voltage level is needed, certain moisture level is needed, like that. So high electric stress present at voids, contaminants, and protrusions is generally believed to be enough to initiate water treeing in presence of humidity. So there are certain processes identified: electrophoresis, polarity dependence. Of course, it depends on the polarity also. Frequency of the applied voltage and temperature also it depends. Chemical composition of the dielectric, pure water is there, or some salts are there. And electro-osmosis. Osmosis means it's a penetrating ability of the water under electric field. So these phenomena will cause initiation or inception of water tree, and it propagates in a particular physical shapes. Of course, bouquets will appear at the needle tip, and they slowly propagate under the electric field over a long period of times, and ultimately breakdown will occur at the end of the propagation. So Professor Tanaka says that water in the microvoids undergoes thermal expansion in a high electric field region by Joule heating, which may bridge the insulation matrix and cause the breakdown. And another person is also from Japan, Yoshimura, observed that dielectric heating leads to evaporation of the water, which may form microcracks and cause mechanical fatigue and consequently electrical breakdown. Of course, these are just understanding of the breakdown phenomena. Of course, whenever breakdown occurs, there must be some high electric field and which will cause an uncontrollable current to flow and an uncontrollable heat to be developed. That's what results in a breakdown in general. And what are the characteristics? Of course, characteristics, low inception voltage compared to that of electrical treeing. Electrical treeing needs higher voltages for inception. But in case of water trees, the growth is very slow. And moisture is necessary for initiation. And we dependent on voltage and temperature gradient also. Of course, tend to temporarily disappear on drying, but however regain original shape on restoration of moisture, etc. So this is typical characteristic of water trees. Method to reduce. You have to use perfect sheath, so impervious metallic sheath preventing moisture ingress, and smooth electrical interfaces at shields, conductor, and then insulation shields. You have to use shields, very smooth shields. Addition of fillers, of course, even nano fillers people are trying. Controlling spherulitic growth to have a smaller cavities, etc. And gas cure system over steam cure systems to reduce residual moisture. In steam cure system, for curing the cable, we need to put high temperature using steam or using gas. So steam curing is more conventional actually, but which will have some additional moisture, residual moisture in the cable. So to avoid that, maybe gas cure systems to be used. So increasing density of LDPE and cross-linking, which leads to increase in water tree inception voltage. So voltage levels, inception voltage levels will increase with cross-linking. So these methods may be adopted to reduce the water tree. Now next is electrical treeing. Electrical trees do not require moisture or water. So they grow at sharp edges like this. You can see here there is a sharp needle. At the tip of the needle you can see how the electrical tree has grown here. And similarly, these are all laboratory grown, of course. You can see how beautifully the tree has grown here. So, but of course it is not beautiful to have trees inside the cables. So introduction, in contrast to water trees, electrical trees are characterized by distinct and hollow channels that form inside the insulation. An electrical tree is initiated by high divergent electric field at stress enhancement geometrical features such as a protrusion or due to partial discharge occurring within a gas filled voids. So the electrical trees will originate at three places basically: at conductor screen, and then at outer insulation screen, and then inside the insulation. But at both conductor screen and insulation screen, what will happen? Sometimes the strands, one of the strand may be broken, or there may be a sharp protrusion into the insulation. So that is where the radius of curvature will be very small, and since the radius of curvature is very small, there the electric field will be very high, and that will start the initiation of a tree. So at conductor screen also it is possible, and outer insulation screen, outer semiconducting screen, what will happen there also? Sometimes uneven material distribution may happen on the cable, on the insulation surface, where there may be a sharp curvature into the insulation. So there also the electrical tree is possible. Apart from these two edges or boundaries, internally also tree initiation may take place where there is a void. Void means an empty place in the insulation. Due to in the manufacturing process itself, some void formation is possible. So at the boundaries of the void, the electrical field will be high. So this will result in partial discharges, of course. I'll tell you briefly what partial discharge is later. So due to this partial discharge over a period of time, the degradation will take place and the tree initiation may occur, and ultimately the tree may end up in a failure also. So these three kinds of trees are possible, electric trees are possible. Electrical trees may also be initiated under short circuit and polarity reversal of DC fields, where during the polarity reversal, of course, high transients are expected. Due to that also, the voids may result in breakdown, or at a high sharp edges, high electric field may occur. That may result in beginning of initiation of tree. So possible reasons for initiation: mechanical damage due to high electrical stress, fatigue cracking from polarity reversals, and electron injection which may ionize the polymer, causing chain scission or decomposition and eventually a cavity formation. So this is what Professor Disado has written in this paper. So these are the possible reasons. And then tree initiation. It has been observed that electroluminescence precedes the onset of partial discharge current pulses. So some people have investigated electroluminescence. So before the tree initiation, before the onset of partial discharges, so electroluminescence has been observed. They have measured it also. It is an indicator of the processes involving injected charges which impart energy to the molecular states of the polymer. So that is correlated to injected charges imparting energy to the molecular states. So tree initiation under DC stresses. Of course, AC stresses due to alternating fields. So whenever the field crosses the breakdown strength of a void, the breakdown will occur inside the void, or whenever the tip field increases beyond the breakdown field of the material also, there the material damages and then tree initiates. But under DC stress, DC is a continuous stress, right? It's not alternating. So tree initiation under DC stress relates mainly to space charge accumulation. So, but here the space charge accumulates slowly over a period of time. Due to space charge accumulation, the electric field, which is otherwise non-uniform, tends to be, tends to be non-uniform due to space charge. Means, somewhere the electric field is reduced and in some other places it gets increased. Due to this, and also it will change dynamically. Whenever polarity reversal occurs, electric field distributions has to reverse actually, and it has to redistribute itself. During this transient, it may cause field enhancement and then may result in the breakdown or tree initiation. So it has been observed that tree initiation is more rapid and probable under influence of negative DC stress related to mobility, because electrons, these conducting the particles that move physically are electrons only, not positive charges. So there is a difference in mobility. Therefore, under negative DC stress, the tree initiation is observed to be more rapid. And propagation, partial discharges starting from protrusion extend, forming branch or bush-like channels along the path with their tips at the highest electric stress. Now, how it propagates? For example, you see this is a needle. So the breakdown initially takes place at the tip of this field, and it forms a channel, suppose. At the end of the channel, what will happen? Again, the radius of curvature will be very small at the end of the channel again. And this channel becomes carbonized and it behaves like an electrode only. So, in fact, the breakdown channel behaves like an extended electrode. So, at the tip of the electrode, again the electric field will be high. So, again it will cause the next breakdown phase. So similarly, the channel goes on extending and lengthening and then ultimately reaching the other electrode, so where it breaks. Of course, certain channels may not progress. So this all depends on the length of the channel and then relative resistance of the channel. So therefore, if there is an easy path to the electrical field or electrons, they will definitely follow that easy path. They will not go through, means, wherever the resistance is high, if they are facing high resistance in a particular channel, then definitely they will stop moving in that channel. Obviously, the low resistance path they will choose. That is how the tree, ultimately progression or propagation depends. So it moves. Of course, it is statistically dependent. Also, it is a process. It is a stochastic process in which the direction you cannot say that shortest distance is the channel. In that only it has to move. No, it will not happen like that. It will go through a weakest path rather than shortest path. And weakest path depends on the material structure. Irrespective of the uniformity of the material, definitely there will be non-uniformity inside the material. So there will be a certain channel which is the weakest among all the channels, and then the breakdown will occur through that channel only. So this is how the tree propagates and finally breakdown will occur.
Sir,
So
one
here,
small question here, sir, if I may.
yeah.
Sir, the tree channels, sir, in the voltage in the tree channels, will that be equal to the voltage at the needle tip, or will there be a gradient along the tree channel, sir?
What did you say? Weightage.
The voltage at the tree channel, will that be equal to the needle voltage,
Yes. Tip
or will
voltage.
there be a gradient along the?
A little bit, even if the gradient is there, it is actually a conducting channel. It is a carbonized channel actually. So you don't expect much gradient along the needle tip. So almost the same voltage, same potential will be there at the tip of the channel compared to this. So you cannot expect a huge gradient. Of course, without gradient, nothing, even in conductor also gradient will be there. So you can expect very little gradient from needle tip to the tip of the channel. And that's how it propagates.
Okay, sir. Thank you.
And this is a typical experiment conducted in our lab actually. You can see how tree initiation is taking place here. At 1 kV per minute, experiment is conducted. Inception started at 14 kilovolts. And tip plane distance is 2.5 mm. From here to here, it is 2.5 mm. This is experimental setup. At IIT Ropar, we have this one. Here you can see there is a sample in which needle is inserted. This is the electrode, and these are the voltage source connected to voltage source, and here this is connected to ground. This is a camera, and here there is a microscope which will zoom this one, and then which is recorded in this. So by physical observation, we can see when the tree is initiated. But of course, for observing DC, it is very difficult because DC is a very fast phenomena and breakdown occurs suddenly. The tree initiation, growth, everything happens very suddenly. And in case of AC, you can see these tree channels very clearly because, the AC being alternating, you will be, damaging the material slowly or in certain channels. But in DC, the voltage will be always at same level. So when the damage occurs, the damage is very sudden and then it is complete breakdown will occur. So for AC and even for impulse also, tree initiation can be easily observed even in a laboratory. So these are the typical types of electrical trees available in this book. And electrical treeing from water treeing. It's also possible an electrical tree may result in a water tree. The moment water is absorbed in some place, then ultimately it becomes a water tree. So this combination of trees is also possible. And ultimately, breakdown and failure results in a, whenever there is a high electrical stress, then the material can withstand. That is known as intrinsic strength. And then whenever there are sharp edges and then formation of trees, this is practical breakdown. So it doesn't depend on intrinsic strength, of course. It is commercial breakdown, what it is known as. So to understand the actual commercial breakdown, actually we have to do experiments with the needle tip arrangement. So the breakdown strength testing methods involve, needle arrangement and then the electric layer like this and testing the breakdown. The breakdown strength depends on the radius of curvature of the needle tip actually. So with different kinds of radius, with different values of radius of curvature, we have to conduct the experiments and then find out the breakdown strength at a different radius of curvature. And the things which affect the breakdown strength ultimately, variables that must be controlled to ensure that reliable data is obtained are, sample thickness, pre-treatment of the specimen, and then temperature of the test, environment, relative humidity, of course, electrode nature, the rate of rise of applied voltage, whether you are raising the voltage. See, these are all essential factors which are to be taken care while deciding the breakdown strength. You have to follow standard procedures to find out the breakdown strength. Rate of rise, for example, if you apply, you have to ultimately increase the voltage to find out the strength of the material, breakdown strength. But in what rate you will increase, whether you apply ramp voltage, whether you apply step voltage. If you apply step voltage at how much time, how much voltage rise you do. So these are all things are important. And the test frequency, one can employ DC or 50 to 60 Hz or impulse voltage. So like this. So this how the breakdown strength is decided. And then partial discharges, I told you just before. What are partial discharges? Partial discharges are discharges inside a void actually. Void inside in the insulation. This is the insulation matrix. You can see there is a circular void, spherical void is given here. So what will happen due to the different in dielectric constants of this void and then this material, there will be electric field, high electric field inside the void, and at the same time the breakdown strength of void is less because it is made up of gaseous insulation and then this surrounding is solid insulation. Therefore, this breaks frequently. So whenever alternating voltage is applied, every cycle you can expect a lot of breakdowns within this channel. So over a period of time, these continuous breakdowns will carbonize the surfaces and they may ultimately behave like sharp electrodes, and then a tree initiation may take place. Either direction it may happen, and then it may ultimately lead to breakdown. So these discharges which occur inside the insulation, they are not complete discharges, because complete discharge means the discharge connecting this electrode to this electrode, that is a complete discharge, means that is breakdown. So these discharges are limited to a void only, voids only. So that's why these are called partial discharges, or partial breakdown only will occur inside the insulation. So these depends, the inception voltage depends on the geometry of the void, how big it is, etc., and what are the dimensions, and then location of the cable wall. So where exactly these are, whether they are close to the cable wall or whether they are inside, and then void size, of course. Geometry means it comes under size also. So these factors will affect the inception voltage. Inception voltage means at which the partial discharge just starts to occur. or breakdown of the void starts to occur, that is inception voltage. So these factors will affect the inception voltage, and partial discharges are very, very important actually. All commercial equipment are supposed to break due to partial discharges or age due to partial discharges. Ultimately, the failure is believed to be partial discharges. Of course, these will happen at voids, and then apart from partial discharges, protrusions of materials, protrusion of conductors, so sharp edges, and then foreign materials such as, in the insulation, there may be sometimes conducting particles, some due to some accidental, dropping of materials, or even while manufacturing process, even though you maintain, clean room kind of environment, even then human hair also may fall into the insulation. So these fibrous materials, all these will ultimately result in failure over a period of time. So apart from the partial discharges. And power cable installation, just I will show one slide how the installation is done in trenches, and then you can see here, separately the cemented trench they have made. Of course, this simply in the they dug in underground, and then they put the soil on this. So it depends on the nature of the soil and then environmental conditions. So, for example, if a corrosive soil is there, then you have to take adequate measures to lay the cables. And if the thermal properties are not favorable, sometimes you have to make trenches and then fill the material with different material which will have good thermal conductivity. Otherwise, cable temperature will rise, and then we cannot use it for high current capability. So there are non-flexible cables and flexible cables. Of course, non-flexible cables, there are problems actually. You cannot put long lengths, and you cannot bend them. That is the problem. And flexible cables, you can even keep on drums and then lay them very easily. So there will be less joint for meter length. So, but here the high probability of mechanical failures, because you are bending the cable so many times on the drums also, and while laying also. So there may be mechanical failures in this case. So this is about laying and power cable manufacturing, how they are manufactured. So this is a conductor, annealing, drawing and wire drawing and annealing process. So there is here you can see the wire is going through a draw plate through this. So this is the specified diameter actually, whatever is required. So here undrawn wire is of this much width. So initially they will hammer and then insert through this, and then after that they pull it. So automatically wire becomes of this length. At a particular temperature it has to be operated. So the wires, you can see how they are made, strands here. This is 17, this will be rotating actually. These are several wires are coming here, and they will be systematically being laid on the central conductor. So like that stranding is done. So this is about wire stranding. And then how the material of insulation and several layers are laid. This is what is known as extrusion process. So for extruded cables, this is extrusion actually. Here you can see there is a bowl here in which the pellets are dropped in this, and the pellets will melt, and this screw will drive it, and then there is a to die take off. So from this cable is drawn, and along the surrounding the cable there will be the insulation material will be laid on that. Not only insulation material, in triple extrusion process means in the three materials will be simultaneously put on the cable conductor. So on the conductor, so the here conductor shield first, and after that insulation shield. These are all melt materials will be will be put on the cable. So here, and the third one is, this insulation sheet. These two are semiconducting materials, and the central one is insulation material. You can see from the cable, the conductor is moving like this. The conductor is moving like this. As the conductor is moving, first here it is the semiconducting layer above that, and above that this insulation layer, and above that finally the again semiconducting layer, which is above the insulation it is. So like this complete cable is manufactured. So this is about manufacturing process of extruded cable. Of course, paper insulated cable, you have to wind the cable and all. So that is a different story. And the next important aspect is the termination of the cables. So how to terminate? Ultimately when you are using cable, the cable is to be connected to a overhead transmission line somewhere else. So when you connect a cable to a overhead transmission line, then it is not direct. You cannot simply open it and then conductor, you cannot connect like that, because due to high electric field, high voltage at the conductor, and the distance between the conductor and outer insulation is very small. So you cannot simply cut it and then connect. So there should be certain arrangement to connect to the overhead transmission line or substation or any load. So like that you can see this kind of structures. So this is cable actually. This is a structure which is known as termination, and this is again the open conductor again here. So this kind of structures, of course this is very small, looking very small. Very huge structures will be there for very high voltages. So this is how the terminations are done here. So this is stress cone termination. In stress cone termination, you see this is the cable here, and this is also cable, but here the outer semiconducting layer is removed. So only insulation material is here, and centrally there is a conductor. Now high voltage is here and ground is here. So you can see this is high voltage, this is ground. Therefore, over the surface also there is some surface currents possible, and then ultimately they may reach here. So, and the electric field lines will be very sharp at this edge. You can see carefully. Electric field lines are very sharp here, very crowded here. So here the breakdown will occur at this edge. Even I have observed physically. So if you open like this and then connect, the breakdown will occur here. So in order to prevent the breakdown at this corner, so there is an arrangement known as a stress cone arrangement. This is cone shaped actually, because if you imagine 3 dimensions, it looks like a cone. Therefore, this kind of arrangement is used. The stress here, the semiconducting layer is not stopped here, but is extended here like this and like this, so that the electric field lines will become like this. They are not now so crowded at this edge. So therefore, it prevents the breakdown. So this is what is known as stress cone termination. You can see this kind of arrangement at the bottom of the termination. Here, this is a stress cone actually. This is stress cone. And then the conductor goes like this, and here it will be opened into the air. So this distance is known as creepage distance.
So won't there be any loosening of the conductors, sir, in the cone arrangement, sir?
Loosening
of the conductors inside, sir? Full cable, sir, expands, or only a portion of the insulation is being expanded?
Yeah, here it is removed, and then there is a stress cone like this, and actually here he has not shown anything else actually. This entire arrangement will be put in oil, and then oil and then bushing type of arrangement, So that kind of arrangement will be there beyond this place. or in polymeric insulation, or in modern silicon insulators may also be like this. This is a silicon insulator.
I see.
So, but above this, porcelain insulators are also possible, but with oil it is filled, and this outer conductor will be at the edge of the oil, or it will be actually placed vertically. All terminations will be placed vertically like this. So at the edge or at the top of that, it will be opened, and when there is an opening, actually there is a spherical structure, or the electrode will be of huge diameter actually, in order to prevent the corona and then flashover, etc.
Like we have a guard ring, sir.
Yeah.
Yes, exactly, like a guard ring at the edge.
Thank you,
So this is how stress cone termination is made, and for small voltages actually this kind of termination, instead of a stress cone, high dielectric constant material is used. These are all small voltage level, low voltage terminations actually. So you can see here the cable comes here, and then from here onwards the polymeric material, silicon mostly, is used as termination. So in this, actually this is high dielectric constant material. The concept is a little bit different here. The high dielectric material can be imagined as capacitors like this, which will cause voltage gradient from this high voltage to low voltage or ground terminal, and thus preventing the failure at this corner. So this is another method of termination. So these two terminations are used. This is for low voltage termination. The previous one is for the stress cone arrangement, is for high voltage. In EHV, definitely oil has to be used. But I can tell you one secret here. Actually, the termination development is not complete. So even now, a lot of scope for research is there, because for extra high voltages, more than beyond 500 kilovolts, the terminations are, and joints also, of course, weaker points of entire cable installation system, where there more failures are expected. So here actually, when it is dipped into the hile, so the breakdown is occurring in this region, or in this region, of course. In this region also the breakdown is occurring, which is also called triple junction failure. So oil will be there. This is stress cone material, and this is XLP material. So stress cone material is actually rubber material normally used. So rubber, oil, and XLPE. So due to that triple junction phenomenon, three dielectric materials with three dielectric properties and different tan delta properties, etc. So people believe that they may accumulate some space charges and then causing the breakdown here and all. But it is still a research topic for any of you to take up. And then these are the two types of terminations. And then apart from terminations, cables also require jointing, because ultimately you cannot produce a cable beyond a certain length. There is a maximum limit for any company in the length of the cable, not only due to transportation, but also the limit of the production unit itself may be in certain kilometers. Of course, for transportation, you have to put it on drums. You cannot have continuous cable on a drum. So you have to limit the length. But when you limit the length, the cable, when it is laid, ultimately you have to join the cable. So these joints are again weaker points. Whenever you open the cable and joint it, of course, you have seen how many layers are there for a high voltage cable. So whenever you open, it is open to the environment. Of course, people take necessary care to seal it in, do it in a sealed environment and all. But in spite of that, definitely due to the involvement of human beings. So the technical ability of the human beings itself varies. Even though you train them perfectly, but still there may be differences, and then ultimately failures are reported more at joints and terminations, not in the main cable, but joints and terminations. So these joints and terminations, there are several types of joints, of course. So this is the jointing the theory here. So there is inside the conductor is joined like this, and there are two types: crimp type of connection for conductor, and then soldered connection. So this is soldered conductor. Central conductor is soldered, or in this case simply crimped. So, and after that the insulation is put here, and this structure, entire structure, is known as joint. So this is a jacket type. Tape is installed for jacketed cable here. So all layers have to be joined very carefully. So this is a very difficult task, of course. For even paper cables, it is even more difficult. For XLP cables, at least it is easy. Even rubber joints can be used. Pre-molded joints are shown here. And then these are transition joints. Transition joints means the joints which join conventional paper cable to a XLP cable are known as transition joints. So because they are forming as a transition from XLPE to paper insulation, therefore the joints which are used for that purpose are transition joints. Normally these are heat shrink joints, called heat shrink joints, because several tubes are made which are shrunk by putting heat, so that it will fix on the insulation. Of course, this is a different technology. So it depends more on the skill of the human beings, of course. So these giants are more in older cities like Bombay and even older cities of the world, where several years ago, around 50-60 years ago, paper cables were laid. Now those cables are either have to be replaced or they have to be joined with modern XLPE cables. So obviously we have to use such kind of joints. So this is a simulation done in our lab for that transition joint. And again, another kind of joints are rubber block joints. These are, of course, pre-molded joints. These are made in factory actually. And what is done is these are taken to the field and expanded, and then the expansion is removed suddenly so that it fixes on the joint. After joining the conductor, this will be fixed on the cable. So this is very easy and simple technique, and very successful actually. The insulation and semiconducting layers all shown here are all actually rubber materials only. The semicon material is made by mixing the carbon particles into the rubber material. So this is about the cable technology. Of course, it is a one semester course. I try to give you in brief about this technology. So there are several topics actually. You can use them for teaching undergraduate students. Certain of basics can be taken from this. And then for researchers also, there is lot of scope, because the technology is not yet become perfect actually. So, and for higher voltages, lot of scope for research exists. And then the breakdown phenomena is yet to be understood. And the charges that accumulate inside the insulation, that are yet to be understood and then addressed. And there is a scope for improved materials using nanofillers, etc. Professor Sarthi might have taught yesterday about it. And then, so
yes, sir.
here, okay. So apart from that, partial discharges and breakdown in needle tip and even treeing breakdown. All these are only, we have understood only the phenomena, but not completely explained them. So a lot of scope for research also exists in this field. So with that, I close my presentation. If you have any questions, you please feel free to ask.